Okay, so let's start the session. Thank you very much for coming back. This session is called Geotechnical or Earthquake Engineering, one of the subjects that Professor Mitchell has been really sort of pioneering in the after the Loma Prieta earthquake. And I'll start with having Professor Russell Green from Virginia Tech introducing the topic. So, Russell.
All right, great. Thank you very much, Kenichi, and thank to the other organizers for inviting me and the attendees for staying around. As Kenichi mentioned, my name is Russell Green. I was one of Jim Mitchell's students. I'll have the photo showing where I fell in the line, but it was one of the Virginia Tech students. So here is a picture or photo of the graduation. And you can see Jim had 77 PhD students, 69 were at Berkeley, and 8 were at Virginia Tech. And of the Berkeley ones, number 37 was Tom Brandon, who ended up coming and staying his entire career at Virginia Tech and just recently retired. And then in the audience is Professor Baxter, Chris Baxter, who presented earlier. And unfortunately, I didn't list Ning Lu, who's also one of the other Virginia Tech PhD students. But if you look at the photo, you can see me here, and you can see Jim here. And I'm not sure if you can see it, but his eyes are closed, but after having 70-some students graduate, I don't think it was too exciting for him. For the presentation, what I'm going to be focusing on is a couple areas that Jim was interested in. Now, my thesis was energy-based evaluation and remediation of liquefiable soils. In preparation for this, Rob Kayen, who's the second speaker in this session, contacted me and asked what I was going to present on, and I thought that would be a nice topic to present on, not only because it was my PhD and Jim worked with it together, but we were actively working on it before he passed away, to the fact that we published a paper in December of 2023 on the topic. But as a result of having two speakers talking about the same topic, because when I asked Rob what he was going to present on, he said energy-based liquefaction. So I figured I would come up with another topic that would be of interest to Jim, and we did somewhat discuss this, but this wasn't a direct collaboration. And that's a liquefaction evaluation of improved ground. So it kind of ties together the earthquake engineering aspects and the improved ground aspects. So acknowledgements, I actually collaborated on some of this work with Professors Aaron Bradshaw from University of Rhode Island and also Chris Baxter from Rhode Island and Cord Wisman from GeoPeer, and funding from National Science Foundation and also GeoPeer. So liquefaction triggering, I think most of the people are familiar with it, but this was the definition that I put together. Others provided some input, and so it's kind of what my opinion is a more succinct definition of liquefaction triggering, which amazingly has been absent from most of the literature. So it's a phenomena that occurs in saturated, non-plastic or low plastic soils that involves full partial transfer of the overburden stress from the soil skeleton to the pore fluid under undrained or partially drained conditions with a commensurate increase in pore water pressure and reduction in effective stress. And for earthquakes, this is a result of the contractive tendencies at low to moderate strains during shaking. And the significance of this is really the fact if you're decreasing effective stress, you're going to decrease strength. And with that, you could potentially have a bearing capacity failure, which is shown on the left, or you could have potential slope stability failure, or anything else where soil strength is going to be important. So kind of building on what Jorge said about Jim focusing on why, we're interested in knowing why liquefaction occurs, and then how to evaluate it, and then also how to remediate it. And again, this is the focus of the presentation. Now, this isn't a timeline sequence of understanding liquefaction. I've kind of put this together to help understand this question, why. So this figure is from Professor Yaud's PhD work, and what you're seeing on the horizontal axis is shear strain, and you're seeing on the vertical axis volumetric change or change in void ratio. So this is for an unsaturated or drained condition. And this was strain-controlled tests, and what you're seeing is different numbers of cycles of loading, and you're seeing 1 cycle of loading here, 30 cycles of loading here, and 1,000 cycles of loading here. And if you look, you'll see there's 3 different symbols, and these are related to different confining stresses, running from 4.8 or essentially 5 kPa up to about 200 kPa. So the control parameter here was that the relative density was relatively constant, but it was showing that you're going to get the same volumetric strain when you induce a certain shear strain independent of confining stress. If we now transfer this to undrained conditions where you have saturated soil, this is work from Professor Dobry, and what you're seeing on this plot is shear strain on the horizontal axis and excess pore water pressure on the vertical axis. And you're seeing that all these different types of data points, and I'll point those out in a second, really fall into one nice line. And if you look to see what these different symbols are, these are actually different types of soil and slightly different confining stresses. But again, when you see that you put it in terms of strain, things kind of normalize together. So it seems like a strain-based procedure would be the way to go. And the reason for that is because for drain cases, we get the same volumetric strain, and for undrained cases, we get the same excess pore water pressure. And everything seems to kind of normalize, both on soil type and confining stress. However, inherently, the strain-based procedure has to be in an effective stress space. Remember that we're predicting accelerations, which relates to stress. In order to get to stress, we have to go from stress to strain. We need a constitutive model. We need to take into account the softening due to pore pressure generation. As a result, we really can't come up with a simplified strain-based procedure. So this didn't quite come out the way that I expected. That dot's a little bit bigger than it was supposed to be. But as opposed to the strain-based procedure, we use a stress-based procedure. And even though this was proposed before the strain-based procedure, I'm going to analyze it now in terms of the strain-based procedure. So I think most people are familiar with this. What you're seeing down is the horizontal axis is normalized cone penetration resistance, but that could be other normalized in situ test metrics. And then on the vertical axis, you're seeing normalized stress ratio. So this is in terms of stress. And then you're seeing a semi-empirical curve, which gives us our resistance to liquefaction. So if we look at the factor of safety of capacity divided by demand, we have the cyclic resistance ratio that's normalized. That's again predicted with this curve in terms of in situ test data. And then we have the demand, which is in the denominator, which we relate to the intensity of the shaking. And the star on both of these represents normalization. And the normalized factors for this are for one atmosphere vertical effective stress, duration of shaking for a magnitude 7.5 event, which was the Nagata 1964 event, and that's where we had most of the field data to derive this curve from, so that became our reference earthquake. It's also for no static shear stress bias or for level ground conditions. And then one that's not really pointed out, but is very, very important, specifically to this presentation, but also to ground improvement in general, is this actually relates to normally consolidated deposits. And I'll show the significance of that. And specifically what I'm going to be focusing on are these two normalization parameters. And in reality, they're both normalizing it to the vertical effective stress, but also back to normally consolidated deposits. So let's look at this K sigma factor that acts as this normalization. Originally, this was proposed based on laboratory data, and so this was often cyclic triaxial test, but also cyclic simple shear testing. And what you're seeing is our stress load here, normalized stress load here, and number of cycles of liquefaction on log scale on the horizontal axis. And if you perform this for constant relative density soils, performed or reconstituted the same way, you can develop a curve relating to the amplitude of the loading to the duration or number of cycles of loading to liquefy. And again, this is for our reference condition of 1 atmos vertical effective stress. If the conditions you're interested in situ are for a different vertical effective stress, you could perform the same type of tests under that other confining stress, and you'll get a slightly different curve. And if we assume that that stress is larger than 1 atmosphere, typically it's going to fall below. And this K sigma factor that I showed on the previous slide is simply going to be the ratio of these two stresses corresponding to 15 cycles. And that 15 cycles generally is considered the duration for a magnitude 7.5 event, which is our reference earthquake. So compiling empirical data, and this came from a few different papers that I digitized, what we're seeing is K sigma factor on the vertical axis and vertical confining stress or mean confining stress, depending on whether it was cyclic triaxial or cyclic simple shear on the horizontal axis. And most of these studies were performed in support of the design or evaluation of dams, and you're seeing a wide range of data. And so there's considerable uncertainty and scatter in this data, and I'm highlighting the Duncan Dam data here, which is this data points, kind of the green star, because I'm going to show those later, but also that was a very, very detailed study. And there have been regression analysis of the data, but also based on some theory, and this is one of the more modern or recent or commonly used relationships for this K sigma, and this was actually developed by Ross. This figure actually came from the Idris and Bollinger, but Ross developed this a few years earlier in a paper that he authored himself. And what you're seeing is K sigma again on the vertical axis. You're seeing vertical confining stress on the horizontal axis, and Ross broke it down based on different densities of the soil, whereas using indices of penetration resistance, whether SPT or CPT, for different types of curves. Now the question is why do we need this K sigma? And what I want to do is evaluate this back from the strain-based type procedure. So I'm showing 3 plots here. Now I'm using this as an example, but these curves are actually computed from the Ishibashi-Zhang modulus degradation curve. So in addition to just being an example, they're not just drawn curves, they're actually computed curves. And the first one, what I'm showing is shear stress on the vertical axis and shear strain on the horizontal axis, and each plot has 2 curves. One is going to be our reference, which is the black, so that's for the 1 atmosphere vertical confining stress, and the other actually is for 5 atmospheres, and that's the green one. And when you do it just in terms of cyclic stress, you're seeing the green one is quite a bit higher than the black one. If we now put this in terms of cyclic stress ratio, so just normalizing it by the vertical confining stress, so taking that tau and dividing it by sigma prime, what you can see is the curves somewhat converge. They particularly converge at a larger shear strain, which is consistent with the more Coulomb theory or shear strength theory. And you're seeing them converge at other strains, but not completely. Now, if we take this and we further normalize it by K sigma, and that's shown here, so I'm taking that cyclic stress ratio, dividing it by K sigma, what you're seeing is that essentially you're forcing your strains to be the same. So even though K sigma was really evaluated or conceived as kind of an empirical factor, from a strain-based procedure perspective, what it's doing is actually forcing for a given normalized cyclic stress, you're going to induce about the same strain. And again, my contention is liquefaction is strain-based. So let's look at specifically, if it is strain-based, we should be actually able to back calculate K sigma from the modulus curves. And again, this is the Ishibashi and Zhang curves. I'm again using it for 2 different stresses. The dashed one now is my reference. The solid one now is actually for the 5 atmospheres. So let's assume we impose a certain cyclic stress, we're going to get a given strain on it. And what we want to do is again map this back into our reference space, which is 1 atmosphere. So what we want to know is what is our cyclic stress ratio corresponding to the 1 atmosphere confining stress. And you can do that by dividing it by a factor. In this case, this factor is I'm designating it as K gamma. It's the same as K sigma, but what I'm doing is I'm forcing the strains to be equal, such that for a given cyclic stress ratio, I'm going to back out, and for both of these cases, I'm going to induce the same strain, one for the case of interest and other for my reference condition. So what this allows us to do now is actually use these curves to back calculate what K sigma is, or again, I'm going to call it K gamma because what I'm doing is forcing the strains to be equal. And here's a plot. Here is K gamma on the vertical axis. Here's my vertical confining stress, and you're seeing 3 different curves. These curves all can correspond to normally consolidated soils, which I'm assuming K naught is around 0.45, but they correspond to different cyclic stress ratios. So as opposed to assuming my factor of safety is 1, this applies to all factors of safety. So remember from the laboratory case, those curves that they were using was all at the initial liquefaction triggering, which means they only apply really for a factor of safety of 1, as opposed to factor of safety less than 1 or factor of safety greater than 1. And in this case, all of these are for a certain density, but I could plot other curves for different densities using the same approach. So the question is we have quite a bit of empirical data. How well does this compare to the empirical data? This goes back to the Duncan Dam data. So this is just a replot of that data that I had showed for Duncan Dam. You're seeing K sigma on the vertical axis. You're seeing the vertical confining stress on the horizontal axis in terms of atmospheres, and this is the empirical lab data. Well, I should be able to use those modulus curves and back out what K sigma should be for these. And this is what you get. So the red plots now are my back calculated K gamma using the Ishibashi and Zhang modulus degradation curves. So this gives you credence that this approach of what K sigma actually is, even though it was originally just an empirical factor, is really just forcing your strains to be equal. So now we can relate this to ground improvement. And specifically, the type of ground improvement that I'm going to look at is vibrocompaction. And I'm going to focus mainly on vibrocompaction increasing lateral confining stress. And this is a drawing that actually came from my PhD thesis, but it originally was from Hayward Baker. And here's vibrocompaction in practice. And this is the Hong Kong airport being developed, which was a man-made island. So for vibrocompaction, just let me quickly summarize what you do for it. You're inserting a vibrating probe in the ground, typically assisted by water jets. You're getting it down to the depth of improvement that you want. You're letting it vibrate. As the soil densifies, you're now putting in more backfill. And then you repeat this process and you work your way out. So you end up with a column of soil that has increased relative density and also increased K0. And again, the slides got slightly skewed. That circle was supposed to be around specifically focusing on the influence of K0. Now this is typically implemented in a grid pattern if you look at the site in plan view. And so you're densifying the soil. And what I'm going to focus on, again, not is the increase in density, but the increase in lateral confining stress. And if you look at your unimproved ground, you would expect K0 to be lower if it's naturally consolidated or normally consolidated. You'd expect that to be around 0.45. Often what you're doing is performing some sort of in situ test in the center of this grid, so somewhere along this center point. And in this region, I would expect K0 to be higher. And again, using the Ishibashi and Zhang curves, now keeping my confining stress constant at 1 atmosphere, and also my density constant. Again, I'm just focusing on the increase in lateral stress. The increase in lateral stress will actually change by reference curve here for normally consolidated soils to here for over-consolidated soils or improved ground. And so what you're getting is an increase in the shear stiffness, which could be used quantified in terms of Gmax or shear modulus, or also shear wave velocity. And this increase, what I'm focusing on is for improved ground, but it also could be due to increased lateral stress due to aging. So you saw Professor Baxter present previously on the influence of aging, increasing K0. That will also have this same type of influence, maybe not to the extent of ground improvement. So now let's force the strains to be the same. This is the condition we're interested in. This is our reference condition here. So we come in with our applied cyclic stress ratio, we get a certain strain, and the K0 that I used to compute for this was for 0.8, which wouldn't be unreasonable for vibrocompaction at the center point between the grid points. What we're interested in is knowing is what is the factor on our reference condition. So in this case now, even though we're both at 1 atmosphere, our K gamma is actually greater than 1 because our reference curve falls below the curve of interest. So going back to the stress-based procedure, showing the curve again, that should be a much smaller point. But looking at my normalized cyclic stress ratio, this is now going to be larger than 1, which means our cyclic stress ratio is going to go down, which means our factor of safety is going to go up. And as far as the simplified procedure, we started out here, and as a result of the ground improvement or increase in lateral stress, we're moving down here. Both still are falling on the liquefied side, but the overall goal is to decrease this down into the non-liquefied side. So going back to my K-gamma factors, this is what I previously showed for normally consolidated soils. Now I can plot it for just the increased in lateral confining stress. And my K-gamma factors now all plot above 1 up here. So what does that mean from a standpoint of liquefaction triggering? Again, it's going to reduce our cyclic stress ratio, which is going to increase our factor of safety. However, Rodrigo showed the influence of lateral stress on cone penetration resistance. And this is work that Rodrigo did with Ross and also Jim. And this is a plot of K naught divided by K naught for normally consolidated soils. So in this case, the numerator is for our improved ground, the denominator is for our normally consolidated soils, and then this factor CNH relates our penetration resistance for normally consolidated soils, which is our reference condition, to our penetration resistance for improved ground. And what you could end up seeing here is this factor is less than 1. That means that our normalized value will be less than our normalized penetration resistance. So how does that influence our chart? Going back to this chart, we're starting out with penetration resistance here. We've already reduced our cyclic stress ratio as a result of the increase in lateral stress. However, now we need to also reduce our penetration resistance because of our increase in lateral stress. So this actually has a counteractive effect on factor safety, where our K-gamma factor reduced our cyclic stress ratio, which increased our factor of safety. The correction to penetration resistance actually reduces our CRR because we're moving from here initially over to here, and that's going to decrease our factor of safety. So we actually have two competing effects. And in a perfect world, they would both perfectly cancel out, but they actually don't. So doing a parametric study to see the influence, overall influence of increased lateral confining stress, I'm showing plots here of factor of safety for improved ground divided by our factor of safety if we assume that ground was normally consolidated. So we ignored all the influence of lateral confining stress and just implemented the simplified procedure in the improved ground, ignoring again that we're not normalizing back to the reference state. And I did this for 3 different measured penetration resistances, 50, 100, and 150, so loose, medium dense, and dense. And again, this is a function of cyclic stress ratio, and what you're seeing is your factor of safety increases as K naught increases. So I'm showing my reference condition is if my K naught was 0.45, and then I'm showing it up here for a case where my K naught increases to about a factor of 2. As a result, you can see that you're going to be conservative by about a factor of 2 if you're able to get those higher confining stresses. That's if you have a loose or low penetration resistance. That effect is less as you increase in your penetration resistance and actually reverses. So in this case, ignoring the lateral stress is actually very unconservative or very over-conservative for a looser, slower penetration resistance, and is actually unconservative for a higher penetration resistance. So a summary, this study only focused on increased in lateral stress, and that's actually why I looked at fibrocompaction as opposed to stone columns. Stone columns will have the same effect, but then you're going to also have shear stress redistribution. I didn't even include density, changes in density. So this is just showing a factor that we normally ignore, which is lateral confining stress, and the results of ignoring it. But using the simplified procedure and ignoring the influence on lateral stress, you're going to ignore the influence of lateral stress on liquefaction triggering, and then also the influence on penetration resistance. The K-gamma factor mechanistically accounts for both the change in the vertical stress, which is what K sigma did, but also it looks at the influence of lateral stress. And so it's from basing it on, going back to what Jorge said, Jim focused on why, this understands the mechanics of why we're getting this behavior. And then ignoring this influence is conservative if we have a loose to medium dense soil, and is unconservative if you have a denser soil. And with that, this is, John Bray actually showed a photo previously. This was at Ricardo's Dobry's honorary symposium at RPI. Jim and I both went to RPI different times. Couple things. One, I regret that Holly was not in this photo. She was actually present, but it was regret. If you don't know the people, that of course is Jim, Ken Stokey, myself, Ricardo, Jose Rosette, and then Mrs. Dobry. And in addition to, unfortunately, Holly not being in the photo, it also taught me, keep Jose away from your wife. So with that, I welcome the next speaker. Thank you.
So this will be the last technical session by my colleague, Professor Robert Kayen.
Good afternoon. Thank you very much for staying to the session 6. It's really an honor to be here, and a lot of thoughts about Jim Mitchell, wonderful thoughts about Jim Mitchell as an advisor. This is a topic that both Russell Green and I share, in that we both worked on this topic, and it's a very interesting topic because you're at Berkeley and you think Harry Seed when you think soil liquefaction, and of course that's just kind of a magnum opus, a fantastic body of work. But an interesting timing happened, and that timing was that Harry Seed passed away in the spring of 1989. And in the fall of 1989, the Loma Prieta earthquake occurred. And of course, Harry Seed would have been the leader of all of those efforts, but Jim stepped in, and he stepped in a very interesting way, and I'm going to talk about that today. So I'm going to talk about energy-based soil liquefaction triggering approaches. And the interesting thing about this is, of course, everyone knows already from all morning session and afternoon session that Jim's brilliant. He was an amazing researcher. But one of the reasons why we're here is a feeling of love. And we're feeling that love because Jim had other qualities. He was thoughtful to every one of his students and to everyone he interacted with. And you get that feeling all through the day. He was generous with his time. And, well, he was kind. He was a kind person. And for all of us who are teaching or we're in industry, whatever our work is today, some of what we're best doing, I think, is carrying on his personal qualities that were beautiful qualities of a very kind person. And so that's how I remember Jim. And it's like Ed, it's kind of very hard to deal with Jim not being here. Anyway, these are two papers, and these two papers, they're about almost 30 years apart. And of course, the research code went beyond that, but it sort of bookends this sort of range of a whole suite of papers that Jim was involved with in studies looking at energy-based soil liquefaction triggering. So this is an early one, 1997, looking at RAS intensity versus field measurements. And then way down 30 years later, Jim is 93, where he's the co-author of this paper. We're looking at dissipated energy, normalized dissipated energy as a function of field measurements. Kind of fascinating, right? And so he gave us a lot of guidance in this work. I want to talk about these two methods and talk about similarities, differences, how potentially they can be linked together. On the left side, we have RAS intensity. So RAS intensity is really a simple parameter. You get a strong motion record, you combine the energies of the east-west and the north-south record. It's basically the square of the accelerations over time. It includes duration. That's all part of every one of these points is actually a field measurement. We estimated the RAS intensity at depth in the ground. We knew what the N160 was because it was measured in the field. So totally an empiricist kind of approach to this. And then we have a boundary, and that's a clean sand boundary. And it's easy, right? And that's how I got my dissertation done, right? I did it the easy way. Other people are going to do it a much harder way later on. So that is this parameter, and I'll just tell you that it's easy to measure, it's reasonable to estimate, it's a measure of the total load imparted on the soil by the earthquake motion. But it's not the ideal parameter. And why isn't it the ideal parameter? Well, in part because we don't know what portion of that total load on the soil is doing work to soften the soil, to elevate poor water pressures. So that brings us to the plot on the right, normalized dissipated energy. Normalized dissipated energy, we accumulate the area inside the hysteresis, and we normalize it by effective stress. And here we're going to plot it against cone data. So some of the aspects of it are, well, first off, it's actually the measurement we want. It's the work done on the soil that causes the pore water pressure to rise, reach a state of initial liquefaction. But here's the problem with it. It's vexingly hard to measure in the field. It's much easier, but no, it's still hard, to measure in the laboratory or in the centrifuge model. So it's the right model, but it's impractical to work with. And let me give you an example here. So for example, for our field data, we have almost no false positives in this data set, right? So we have earthquakes, from small earthquakes to large earthquakes. We're doing the A squared dt, so duration is factored into it. Great. The false positives over here are all over the place. So what's going on? Well, we have an outstanding group of authors on that paper, so it's no shortcoming of the authors. What's happening here is that every single one of these points is derived from a proxy estimate of what that work would be, not from a direct measurement of the work, okay? So in other words, the authors here were unable to calculate that dissipated work for every one of those field condition sites. So it's a difficult, vexing problem. So the outline of the talk today is to talk about the energy-based methods, and in particular, I want to talk about the ability to predict pore water pressure rise, understand the timing of initial liquefaction, and assess liquefaction potential. Obviously, across the boundary, you're in the zone of potential liquefaction. I'm going to talk about 3 different methods: normalized dissipated energy, spectral energy ratio, and RAS intensity. And I'm going to show you new work, relatively new work, to try to understand and tie these ideas together. Okay, so this is a method of a recent paper where we're going to try to calculate the dissipated energy. So we have first we have ground motions, or in a laboratory setting, sinusoidal waves, or in a centrifuge, loading from the centrifuge loader. And we have our records from which we calculate stress strain hysteresis loops, and we're going to calculate the area inside the hysteresis loops, and we're going to exclude the areas outside the hysteresis loops using trapezoidal integration. Straightforward. Then we're going to use the time histories of pore water pressure rise and relate it to the amount of work done. So we know what the RU is, building up from 0 to 1, and along the time that we're accumulating the work, we're also monitoring the rise in pore water pressures. And so we can get a relationship between the pore water pressure rise and the work done. We do that for the rise in pore water pressures, but we also have dilational spikes. Dilational spikes pull down that water pressure. So for the dilational spikes, we try to look at the shear stress over confining stress, and relate it to the amount of RU reduction for every one of those dilational spikes to predict how much the pore water pressure falls. And this is the kind of data you see here. So you end up seeing both in linear and in semi-log form. We see the pore water pressure rise as a function of work, normalized by effective stress. This is from centrifuge leap tests, and it's for a variety of relative densities. And this is really very much like the work of Kokosho et al. What is this? This is fundamentals of soil behavior, right? This is Jim Mitchell's influence on what's the relationship between work done to soften a soil, to elevate its pore water pressures that lead to a relationship like this. This is our dilational spike method to understand how much the pore water pressures are dropped down. If we look at these data across a variety of tests, so this is 3 of 7 different centrifuge model tests during the LEAP project, and then from which we can make modeled curves to relate the pore water pressure rise to the work done. And of course, we generated these data sets using the LEAP data, so if we throw it back at the LEAP centrifuge results, it ought to do a good job of matching the pore water pressure rise, and it does. So here, the red line is showing you the rise in pore water pressure and the dilational spikes. This is in Japan, and in China, 3 different tests that were run on the LEAP project, and tests were run in Davis and RPI as well, and in England. And we see a pretty good match. There's another method here, a strain-based method I'm not going to talk about today, and it's not working quite as well as the energy-based method. So here's a case where we have these, basically a laboratory condition, a centrifuge test, and pore water pressures are calculated, and the work done by integrating the space in the hysteresis, it's all very tractable. Once we start to take this out on the road, things become really difficult. One of the reasons why they become difficult is the hysteresis loops of real earthquake motions are so unusual and complex and odd, you can go crazy trying to trapezoidally integrate them. They're very odd shapes. So here's the upper layer, north-south, east-west, north-south, east-west for a lower layer. And what we see in the rise in pore water pressure is, at some value of an RU greater than 0.95, a timing of liquefaction, an estimate. So the way we did this type of analysis is we used our LEAP relationship curves, related it to the relative density of the soil at the site, and this is a site in Hokkaido from the 2003 Tokachi-oki earthquake, and we have 2 measurements, but close to 50 seconds, or 48 to 49 seconds, and then 55 seconds for the deeper layer. We have the motions from the Kushiro port site, and when we apply the Stockwell transform method that Steve Kramer developed in 2016, we get very similar timings, 50 seconds and 55 seconds. More on the Stockwell transform in a moment, but these are 2 independent methods that are giving very similar timings in terms of liquefaction response in the ground. The Stockwell transform, this is a great paper by Kramer et al., 2016, and the Stockwell transform is this visual representation that displays the loss of higher frequencies as soil liquefies. The plot on the upper right is a frequency on the y-axis from 0 to 10 hertz versus time. And so the way a Stockwell transform is calculated is time slices are taken, and then the Fourier transform is calculated, and we basically plot it out in terms of its amplitude over time. So the x-axis is the time. So we can see that the frequencies are relatively high before pore water pressures start to build up, and they start to fall very dramatically as the pore water pressure rises. What's going on here? We have basically energy working on the soil, raising the pore water pressure, softening the material, and so that only lower frequencies can be transmitted through that soil mass. What is that? It's fundamentals of soil behavior. It's Jim's influence and Jim's ideas coming through in the analysis of a Stockwell transform, I think. And that's how it's presented here. So this is an idea that I want to, a new idea in terms of how to quantify some information about the timing of liquefaction from the Stockwell transform, and it's called the spectral energy ratio. And what we do is we take the partial area of the Fourier transform, and so it might have peaks in the low frequencies and the high frequencies. The full range here is from 0 to 10 hertz, and we just fix some static spectral energy ratio, 0.5, 0.65, that would be nice. It turns out 0.65 doesn't work very well. Sorry, John. But I would have liked to have seen that work. But in any event, what we're doing is we're picking the ratio of B divided by B plus A, and we're watching how the frequency shifts as pore water pressures rise, the soil softens, and that upper bound frequency shifts down to lower frequencies, and we track it. And that's in contrast to the modal frequency method of Osner et al., for example. So, forward ho, let's look at what that looks like. So this is our frequencies over time. Here's our spectral energy ratio. Here's our frequencies from 0 to 10 hertz, and here's our time, progressive as the pore water pressures rise. We found that the lowest root mean square error to estimate the timing of liquefaction required a spectral energy ratio of 0.92. In other words, that was the frequency at which all the frequencies in the Fourier transform, 92% were below that upper bound frequency. And then we track how it falls as pore water pressures rise. And so here's an example where we have no pore water pressures, and then the upper bound frequency falls and plateaus, and this is given as the timing of liquefaction. So it's at the bottom of that ramp. The modal method, which takes the least squares best fit on the non-liquefied side and the liquefied side, gives us a point typically in the middle of that ramp. It's actually more representative of an RU of 0.5. So here's an example there's about 30 case histories that we've looked at, and by and large, what we see is we get a very nice relationship with Steve Kramer's data set from 2016, and we have many sites where we have longer duration times than Osner et al. And Zhang et al. And we think that they're under-predicting the time to initial liquefaction. Okay, the third method I want to talk about is RES intensity. RES intensity is a really simple parameter, but I want to tell you a powerful thing about that boundary curve that's different from the cyclic stress ratio boundary curve. Energy is scalar and it's cumulative, and that means as the soil comes up to and liquefies, reaches initial liquefaction, we have a certain value, and then it just keeps on rising. It can only go up. And that tells us that the boundary curve in both the dissipated normalized work and also for RES intensity, that boundary curve is the boundary of initial liquefaction. So let's take advantage of that. So here's a data set. This is the Hokkaido data set, Tokachi-oki. When we use Steve Kramer's method, we get a certain timing, and it's something like 50 seconds. And as we track the rise in RES intensity at depth in the layer, it crosses the boundary at a value very close to that, about 48.7 seconds, very close match. And for another layer at Tokachi, a stiffer layer, we see a longer duration to the point of initial liquefaction, and the rise in RAS intensity at that point in time being associated with the crossing of the boundary, 55 seconds. So we have a comparison with the Stockwell transform with normalized dissipated energy and with RAS intensity, 3 different ways to extract information about the timing of initial liquefaction. Anyway, that's how we use RAS intensity to try to estimate the timing, but we can do something else. We can take the whole problem and turn it on its head, and we can try to use the information from the Stockwell transform or from normalized dissipated energy in the model, therefore, and we can estimate what the timing of liquefaction is and then plot new points on the RAS intensity liquefaction curve. So we can actually use the Stockwell transform to inform us about where we should be plotting points for initial liquefaction in the RAS space. Anyway, what does Jim Mitchell have to do with all of this? Well, one of the things that really impressed me about Jim when I first arrived at Berkeley, because I was coming from the U.S. Geological Survey, was, well, he was the most scientific person I could see in the department. Like, he approached all his problems not as an engineer trying to solve a problem, which he did for sure, and we know that's hard to do, but science is harder. Science is harder than that. Science is understanding why something happens. And Jim took that extra step, and that was sort of a very unusual quality of Jim. These are the various things I talked about, so I don't need to cover them again, but I will say that our objectives of this work are, we have an easy parameter, it's called RAS intensity, and we can measure it, but we know it's the wrong parameter. And we have this other parameter, normalized dissipated energy, and it's the right parameter, but it's vexing to use. And what we want to do is try to get the interrelationship between these 2 parameters, as well as relative density and site parameter measurements like N160 or QC1, to try to use RAS intensity as a proxy for the dissipated work. Okay. And these are the references that were in the paper. Thank you for your time.